this is section 2.5, intermediate value theorem and polynomial inequalities. Objectives, the intermediate value theorem. And number 2, approximating zeros using the bisection method. And then polynomial inequalities. So intermediate value theorem, which is we call the IVT. In this chapter, we have been efficiently using synthetic division along with the factor and remainder theorems to factor polynomials and then find the x-intercepts. However, if you recall example 9 from the section 2.3, we found that the none of the possible rational zero from the least from the plus minus 1 to 4a gave a remainder of the zero for f of x equal to x cubed plus 10x minus 10. So, which means your answer is not going to be the real zero. So it's going to be the no, it could be the real zero, but it's not a rational zeros. And then also could be the complex zeros. So we know that this function must have a 3 zeros counting multiplicities. We also know that the non-real complex zeros comes in pairs. Therefore, this function must have at least one real zero. How do we find the real zero when we are unable to find the polynomial function? We are going to introduce the intermediate value theorem that shows how it can be used to approximate real zero of the polynomial function. So this time, we try to get the approximate the zeros, okay? So it's not going to come out nicely. Intermediate value theorem, so for any continuous function f of x and the two value, which is a is less than b, which is a and b are the two number with the x's. This is x values. So one of the x1, the other one is x2. So it's on the number line of x, okay? So it's a x here and y here. So this is x1 and this is x2. So that's what and then we call that as a and b. If you plug it in the function as f of a and f of b has opposite sign, and then the f of x at least one real zero in the interval between the a and b. So which means this value is up here, and then this value is down here. So connecting these two, as you notice, there's a zero between the value of the a and b. So we have already discussed that every polynomial function is continuous everywhere, has a domain of the negative infinity. So that this theorem applies to all polynomial functions. So consider f of x, x cubed plus 10x minus 8. We can evaluate this function for the value x equal to 0 and 1. So if you plug it in 0, and then that equal to negative 8, and if you plug it in 1 of the function we have, and then it becomes, your function, let's write that function because it's under the other page, right? So I plug it in x cubed plus 10x minus 8, and plug it in 0, get negative 8, and then which is a 0 and negative 8, and the other one is 1 and 3. So as you notice, if you plug it in 0 and negative 8 right here, and then 1 and 3 up here, so in order to connect this together somewhere, right, do you see the 0 here? So therefore, the intermediate value theorem guarantees that there is a real zero in the interval of the 0, 1. So before working through another example using this theorem, we need to speak some on how the intermediate value theorem can guarantee the existence of real zero. So when we evaluate the f of x is equal to x cubed plus 10x minus 8 for x equal to 0 and x equal to 1, we found the 2 points that would be our graph of f of x. So if you plug it in, that's what I have, right? So now you have 2 points for plugging in 0 and 1 to get a value. So considering these 2 points, 0 and negative 8, which is going to be below the axis, and then 1 and 3 is going to be above the axis. So knowing that every polynomial graph is continuous, the graph must somehow connect these 2 points in order to travel from the one side of the axis to the other side, then stay connected because the polynomial is the continuous. The graph must cross the x-axis, crossing at a real zero of the function, which means real zero means x-intercept. Okay, so show that the g of x equal to 2x cubed plus x squared minus 3x minus 6 has a 0 between the 1 and 2. So if you plug it in 1, you get the negative 6, which is 1 and negative 6 is below the x-axis. If you plug it in 2, and then it goes 8, which is a 2 and 8, so which is above the axis. Which means connected these 2 points, of course, so there must be at least 1, 0 as a real, okay? Because the g of 1 and g of 2 have opposite sign, the intermediate value theorem guarantees that g of x equal to 2x cubed plus x squared minus 3x minus 6 has a 0 in between the 1 and 2. At least 1, which means it could be more. After that, we have used the intermediate value theorem to locate an interval that contains at least one real zero. We can use the bisection method to approximate the zero, which is, yeah, it's hard to get the the exact zero, but we can approximate it. So when we consider the first function we have earlier, f of 0 was -8 and the f of 1 is 3. So therefore the intermediate value theorem guaranteed that a real zero between the 0 to 1. But what could that be? Okay, we just say, oh, there's a 0 between the 0 to 1. But is that going to be the 0 0.1 or 0 0.15, 0 0.9? So we want to see what it is, okay? So we use the bisection method. We can get approximation for the 0 in this interval. So I'll show you here in the several example, okay? So consider harmonies of 0.5, which is a right middle between the 0 to 1, right? So we use the 0.5. If you put the 0.5, it gives us a negative 2.875. So up to 4.5, I think it still stays a negative y value. And then f of 1 is a 0. So instead of the 0 to 1, I can reduce it as 0.5 to 1. Okay, because this still give you the negative value and this still give you the positive value. Now, between the negative 0.5 and 1, I want to use a 0.75. So if you use a 0.75, it's still going to be negative value. So instead of the negative 0.5 and 1, now I can use a 0.75 and 1. Repeating this process, consider now getting bigger than 0.5. Now I'm using the 0.875. So when I use a 0.875, this becomes now the positive. So instead of the 1 that I use a right side interval, I use a 0.85. So I'm using this one. So if you keep doing that, and then now we're looking for any number between that is a 0.8125, it still give you a positive. So instead of using the 0.875, then I'm using this 0.8125. And then keep going, okay? So your answer is going to be something 0.5 between the 0.8125. So you can find that number from the between the interval to check it out. Therefore, the rounding to the one decimal place, there's a 0. Actually, could do about 0.8. And then, but still approximation, though. We can't really say that exactly, okay? All right, let's do the example here again. So we show that the g of x is 2x cubed plus x squared minus 3x minus 6 has a 0 in between 1 and 2. So I'll find so g of 1 is negative 6, g of 2 is 8. But the middle number between the 1 and 2, 1.5, is still going to be negative. So instead of the 1, I'm using 1.5 right now. And then I'm looking for any number between the 1.5 and 2, which is, what about 1.75? Still give you a positive. Oh, so instead of using the 2, I'm using the 1.75. Now you have any number find between the 1.5 and 1.75, I'm using the 1.625. And they give us a positive, so instead of using the 1.75, I'm using 1.625. And then to find any number closer, so I'm using the 1.5625, which give us a negative. So instead of the 1.5, I'm using the 1.5625 and then 1.625. Okay, so we want to say, okay, so about 0.6 going to be the 0 for this case, okay? Instead of the 1.9, 1.8 like that, okay? In order to allow the somewhat easier calculation with a shorter decimal number, we can choose a point in which interval that is not necessarily the midpoint, okay? But we're starting from the midpoint though. Find the real 0 for this p of x equal to x cubed plus 2x squared minus x minus 5 between the 1 and 2. So p of 1, negative 3, p of 2 is 9. So yeah, definitely there's a 0, at least 1 0 between the 1 and 2. So we are looking for middle number 1.5. Numbers in the intervals 0, 1. What do you mean? It should be the 1 and 2. What am I talking about? Okay. All right, that's a mistake. Okay, sorry about that. And then P of 1.5, you got 1.4. So instead of the 2, I'm using 1.5. I'm using 1.5, right? Yeah, so I'm dropping 2 to use a 1.5. Now you're using 1.3 in the number in the between 1 and 1.5, and then give us a negative, which means I dropping the 1 to instead of I'm using the 1.3 and 1.5. Then keep doing that. So now you got 1.3 as a number, and then I'm using the it's going to be 1.4 number, and then 1.4 plug it in as a positive, so instead of dropping the 1.5, I'm using 1.4. Then between number 1.35 and they're going to be negative, so dropping 1.3, I'm using 1.35 and 1.4. So we just say the 0 will be the approximately 1.14, okay? Yeah, not the 0.14, okay? Alrighty. Okay, so polynomial inequality right now. This chapter has been largely focused on the study of the polynomial functions and equations. The final topics of this chapter will show use of the graph of the polynomial function, specifically the x-intercept of the polynomial functions. The graph of f of x is 2x times x minus 3 times x plus 4. X plus 4 has the following details. So y-intercept means you plug it in 0 for the function to get that, but this time it's a 0. And the x-intercept set each factor equal to 0. And then you get the 0 dose as with the multiplicity as a 1. And behavior, since we got 2x cubed as a leading term, and then the positive number with the odd, and then the left down, then the right up, okay? So the sketch of the graph will be the following by this, okay? So now we want to consider the 4 different inequalities here. So solving the 2x times that is greater than 0, and then the greater equal to 0 for the example 2, and then the less than 0 for the example 3, and then less than equal to for the example 4. So we did the section 1.1 to solve each of these 4 examples can be done by inspection using the graph of f of x and equal to 2x x minus 3 times x plus 4. So example 1 says a greater than 0, which means we cannot include the x-intercept here. So in order to do that, for the example 1, anything is above the x-axis. Okay, so this is going to be the solutions, okay? So I want to say up to from the negative 4 to 0, and then 3 to the infinity. So this is it. This is how you can get this. Now, difference between the example 1 and 2 is an equal sign. So we are include the negative 4 and 0. Negative 4 and 0, and then 3. But infinity is always open things. Now, example 3 has less than. So if you look at the less than parts, which is a less than is this is less than, this is less than 0, right? So from the negative infinity up to the negative 4, and then 0 to the 3. So this is it. And then difference between the 3 and 4 is equal sign, so we are included. So negative infinity, negative 4, 0, and 3 is going to be the bracket for this one. So here's a summary for the answers, okay? So you can see that. So you can find the answer from the graph. There need to be 2 important takeaway from this. For example, each of the inequality compare the polynomial function to 0. This is necessary since every function equal to 0 on the x-axis. And our interpretation is to find which side of the axis our graph resides. Each of the answer involving the x-intercept of the polynomial function. So this happens because the polynomial graphs can continue continuous, and they can be only crossed from the one side of the x-axis to the other by passing through the x-intercept. So using these 2 principles, the general process of solving a polynomial function is follows. So number 1, compare each polynomial function to 0, find the x-intercept, draw the sketch of the graph, and then sketch the answer, paying attention to the include or not include the x-intercept by the equal sign. Alrighty, so let's try this, okay? So example 1. So I need to subtract 12 both sides to get 2x cubed plus 3x squared minus 23x minus 12 greater equal to 0. So first of all, we have to find the zeros, okay? So in order to find the 0, first of all, I want to make that as equation, okay? So 2x cubed plus 3x squared minus 23x minus 12 equal to 0. So possible rational 0 will be as plus minus factor of 12 over factor of 2. So which is 12 has a factors at 1, 2, 3, 4, 6, and 12. And then 2 has a 1, has a 1 and 2. So if I see it as a plus minus 1, 2, 3, 4, 6, and 12, and 1/2, 3 over 2. That's all, right? Now we want to check it out. So when you check it out, as here, but you can use the Descartes rules to find actually the change of sign. So change the sign for the f of x if you think this is f of x, okay? And then you got 1, which is there's a 1 positive zeros, okay? So I want to check it out which one that is, okay? So check it out with yeah, this is time consuming, okay? So 2, 3, negative 23, negative 12, and then use 1 and drop to 2, 5, 5, negative 18, negative 18, negative 30, which is not equal to 0, so 1 doesn't work. And then 2, 3, negative 23, negative 12, and then I want to divide by, let's see if I can get a good guess. I want to do 3. And then I get as 2 dropped, and 6 and 9, 27, 4. Oh, yeah, we got a 0. So lucky, isn't it? So 3 is a 1 of the 0. And that means now you got the 2x squared is a quadratic. Quadratic is always kind of solvable as equation, okay? But good thing is, this is still factorable. So this factor as 2x times x. And then I need to get a 9, so plus 4 plus 1. And then you get another 0 as negative 1/2, and then negative 4. So there are 3 zeros right now. So plug it in. So negative 4 is about here, negative 1/2 about here, and then 3 is about here. And then there is also equal sign, so we're going to include it, okay? So all the 0 is going to be included as a solution set. And then the leading term, right? Leading term is 2x cubed, which means a sub n is 2, which is a positive, and then degree is a 3, and then which means what? We have right side up and left side down, right? So from the 3, 0, it goes up, and the negative 4 is down. And also, everything is a multiplicity 1, so you're going to get this kind of graph, which is going to be this, to go back here, isn't it? Yeah. So this is a similar graph, okay? Now we are answering it, okay? So we are answering that is inequality is what? Greater or equal to 0. So we're just gonna find what parts of this polynomial is above the 0. So this is above the 0 and this is above the 0, right? So as a C, we wanna say from negative 4 to negative 1/2. And then also 3 to the infinity is above the 0 as a union. So this is the answers for these questions. Alright, let's try one more. Good thing is, next problem is already the factor form, so you don't need to worry about factor, okay? So I found the 2, 0 here, right? So if you set it up, negative 2x of x plus 3, x minus 1 squared equal to 0. So zeros are x plus 3 equal to 0, x minus 1 equal to 0. But that's a multiplicity, right? So one is a negative 3, the other one is 1, right? But this is a multiplicity 1. This is a multiplicity 2. Okay. And then what is the a sub n? So a sub n, you got to multiply from the negative 2x times x squared. Okay. So a sub n is negative 2 times of x times x squared. I got negative 2x cubed. Oh, so this is a cube. A sub n x cubed, right? So a sub n is negative 2, and this is degree, right? So you get this kind of graph. Okay, so we got the 2, 0, which is a negative 3 is another 1, 0, and then the 1 is 1, 0, right? Isn't it? Okay, and then that's a 0, right? Okay, so and then it's gonna be this to this, okay? And then negative 3 is a multiplicity 1, which is a crossing it. Then you might touch some of the y-intercept somewhere and go up. Yeah, that's all. And then we are looking for that is a less than 0, right? So what parts are less than 0? This is a less than 0, and then this is a less than 0, okay? So which means 1 is equal to 0, so we cannot take that, okay? So from the -3 to 1, and then 1 to infinity is all less than 0. So that's the solutions. Okay? Alright. Thank you for listening.